Hello, myself Muhammad Tajuddin. This is a video about a small topic, the chemistry and physics of the muscle. My dear friends, the biochemistry of muscle is based on the enzymatic activity of meiosis. Its ability to catalyze the hydrolytic cleavage of ATP, and the scheme of the reaction as follows. At we see in the peak, M muscle plus ATP is equal to myosin plus ATP, which is equal to myosin into ADP plus phosphate, which is myosin plus ADP plus phosphate. This reaction is strongly depends on the ionic medium, on the presence of divalent cations. In the muscle, it occurs at the pH 7.4. For the reaction to proceed in vitro, it is necessary calcium ions be present in its optimal, with the concentration of these ions being equal to the concentration of ATP or somewhat greater. The magnesium ions inhibit the ATPase activity of myosin in vitro. In the muscle, myosin functions upon interaction with actin, as has been pointed out, through HMM bridge in the actomyosin complex. Under those conditions, the magnesium ions exert an activating effect. Thus, for the ATPase activity to exhibited in vivo, both calcium and magnesium ions are required. The activation of the striated muscle occurs as a result of transmission of nerve impulse to it. Muscle contraction can also be initiated by an artificial electrical pulse. The action of the impulse leads to increase in the concentration of calcium ions, which interact with a fibril. Each fibril is enwrapped by a complex system of longitudinal and transverse thin tubules known as sacroplasmic reticulum. It has been proved with the aid labeled calcium 45 atoms, the transmission of nerve impulse can cause extrusion of calcium ions from the reticulum into gel-like cytoplasm, that is sacroplasm, which surrounds the muscle is very low, probably less than 10 to the power minus 7 to 10 to the power minus 8 myosins. Upon the activation, it increases 2 into 3 orders. The reaction given on the page 417 accompanied by the subsidiary reaction is called Lohmann reaction, which is ADP plus phosphocreation in the presence of creatine kinase enzyme, which forms ATP plus creatine. It is proved that ATP is split just upon contraction of the muscle. Fluoronitrobenzene inhibits creatine kinase and stops the Lohmann reaction. At the same time, it does not affect muscle of this enzyme. The ATP is split during single contraction and tetanus contraction. On the other hand, the reverse reaction formation of phosphocreatine from creatine can be blocked by iodoacetate. In such case, the consumption of phosphocreatine characterizes the amount of ADP formed during the contraction. The amounts of ATP split on contraction correspond to the loss of phosphocreatine in Lohmann reaction. The relaxation of muscle to its initial state is determined by the expulsion of calcium ions from the sacroplasm into the reticulum. Thus, the calcium ions regulate the contraction process in the muscles. Presumably, this occurs with the direction participation of troponin and tropomyosin. In the absence of calcium ions, troponin complexed with the tropomyosin inhibits the interaction of actin-myosin bridge. The calcium that enters to the sacroplasm binds to troponin and suppress the inhibiting action. Hence, calcium ions play the role of depressor and switch the thin filament over the inactive to the active state. The experimental procedure of corresponding measurements was developed the classical works of Hill and latterly repeatedly improved. Figure 12.13 shows the experimental setup. The muscle M is attached to the one end of the lever. The other end of the muscle is tied to a rigid support. Contraction is stimulated by electrodes E. When isotonic twists are to be studied, the muscle is loaded at position P. The tension is recorded by the means of the tension transducer T at position A. When isometric tension is measured, the transducer is switched over position B. The isotonic shortening is determined by the movement of the other end of the lever recorded by means of the photocell PC. The stop S is controlled by the electromagnet EM, is used to hold up the contraction at any desired length or release an isometrically controlling muscle to any desired extent. Experiment with the frog sartosis muscle shows that during first 50 millisecond after the excitation of an isometric contraction, there occur a series of changes determined by the release of calcium ions to the sarcoplasmic reticulum. Here, the tension begins to increase, reaches its maximum after 170 milliseconds at 0 degrees Celsius. Then it declines, disappearing completely more than 1 second. During the isotonic contraction, the shortening is diminished with the increasing load P. The maximum is attained the earlier, the larger the load, then relaxation to the initial state takes place. The development of isotonic tension is in the muscle practically follows the same time course as development of an isometric tension. Hill has empirically established the basic characteristic equation in the mechanics of muscle contraction. It relates the steady state velocity of an isotonic contraction V to the force P has been hyperbolic form, which is P plus A into V is equal to B into P initial plus P, where P initial is a maximum isometric tension developed by the muscle or maximum load against which the muscle support without shortening. A and B are constants. At P0, the velocity of shorten is maximal. V max is equal to B by PA by A. Conversely, at P is equal to P0, we have V is equal to 0. At P is greater than P0, the muscle is touched. This touching does not obey equation 12.12, which is P plus A into V is equal to B into P0 plus P. The constant B, which has a dimension of velocity, increasing rapidly with temperature. On heating 10 degrees Celsius near 0 degrees Celsius, the constant B is doubled. The constant A varies from 0.25 P0 to 0.4 P0. Hence, Vmax is 2.5 to 4 times greater than the B. And figure 12.14 is the graph which is the dependence of the maximum force of the length of the sarcomere. The solid line represents the data of Edman, and the dotted line is the data of Schoenberg and Poladisky. So, the mechanical energy of a muscle can be defined as the ratio of work done to the energy. In the contractile phase, eta reaches 45% in the frog and 75% in the tortoise. It's in an ideal cyclic mechanochemical process does the work, and the free energy remains the constant. So, the value of eta characterizes the deviation from the degradation in the chemical energy into the heat energy. So, that's all about the mechanical energy and the velocity and the contraction force about the muscle. That's all. Thank you.